everyone, and welcome to this episode of the Foundry Fireside. My name is Mika Ketz-Nelson, and I'm an intern with the Foundry Communications team. Today, I'll be chatting with one of the Foundry's postdocs, Christina Boukouvala. Christina works at the Foundry's National Center for Electron Microscopy, and her work currently focuses on understanding plasmonic aluminum nanoparticles. Thank you for joining us, Christina.
Thank you for having me. This is very exciting.
Can you tell me a bit about your research?
Yeah, so my research focuses on what we call plasmonic nanomaterials. And these are materials with sizes a million times smaller than a grain of sand, which can interact strongly with light. So, how do they do that? Imagine that you have a gold nanosphere and you shine light on it. This is an electromagnetic wave. It oscillates back and forth, and it causes the free electrons of our nanoparticle to also oscillate across our structure. So at certain colors or light frequencies, these oscillations become resonant, so very strong, and so our particles will scatter strongly the light of that particular color. And a good analogy to this is a radio. We broadcast many radio frequencies, but we use our radio circuit to sort of pick up and then amplify just a single frequency. That's the one we are interested in listening. And these nanoparticles do exactly that. They operate like optical antennas, light antennas, and they amplify that specific color. And as many oscillating systems that we are familiar with, think guitar strings or a swing, these oscillations will decay with time. And in doing so, they dissipate energy via different mechanisms that eventually turn into heat. And so, what is exciting here is that all these phenomena are extremely localized on the nanoparticle surface, and we can take advantage of this to manipulate processes down to even the molecular level. So, for example, we can use localized electric fields to sense molecules or the various decay mechanisms to power chemical reactions. And so to get back to my work very specifically, to design structures that manipulate light the way we want them to, we first need to understand how the material composition and morphology will affect this phenomena. And in my work, I use both theory and experiments to sort of understand these relations. At the Foundry in particular, I'm currently focusing on understanding how plasmonic aluminum nanoparticles heat up when we shine light on them.
Thank you so much. What made you drawn to this field of study to begin with?
Yeah, so I first learned about plasmonic nanomaterials during my master's, and what struck me was the very bright colors of these particles that are nothing like the color of the corresponding material we are familiar with. So think about gold. We associate this with a shiny gold, like yellow color, but gold nanoparticles can be red, can be blue, can be green. And so I was really curious to understand how we can control this. And this inevitably led to understanding the shape of the nanoparticles, what is their crystal structure, how we can model it. And of course, as I learned more and more about the field, it also became clear to me how important it is to understand structure property relations if we are to tailor these nanoparticles for various applications.
That's really cool. So, how did you start out in this field?
I had a slightly unconventional path. So, for my undergrad, I studied mechanical engineering back in my home country in Greece. Um, and I specialized in aerodynamics, mostly because I really loved sailing at the time. Well, I still do. However, I was always interested in the things we cannot really see with our bare eyes, from the world around us. And so, in the last year of my studies, I managed to convince my department to let me do a dissertation on nanomaterials, basically. And that was actually in a different school within my university. And I really liked it. And to learn more about this field, I decided to then pursue a master's degree. So, for this, I moved to the UK at the University of Cambridge. And this really was my ticket to a PhD in nanosciences and more particular in the field of plasmonics. Um, in my PhD, I did a lot of nanoparticle crystallography studies, a lot of electromagnetic simulations, and optical microscopy. And towards the end of it, I was also given data sets from electron microscopy to work with. And I became really curious to learn how that data was actually acquired. And this is why I decided to come here at the National Center of Electron Microscopy in the Foundry to learn more about these techniques.
So, moving into your current research, what do you use to achieve such precise changes to your samples?
So nanostructures can be made either top-down, where you start from a block of your material of interest and you sort of eat it away with various methods, or bottom-up, where you literally start from single atoms that you grow into nanoparticles. And bottom-up methods are, I like to think of them like nanoscale machining in a way. You have great flexibility on what nanomaterial shape you can get, but your particles are generally stuck on a substrate and you don't have great control on the crystallography. In my current work, we actually collaborate with the fabrication facility at the Foundry, and they fabricate our aluminum nanostructures for us in the designs that we ask for. On the other hand, nanoparticle growth obeys very strict rules that dictate the nanoparticle shapes we can get. So for example, a cubic material like gold likes to make cubes or octahedra, but a material like magnesium, which has a hexagonal crystal symmetry, prefers to form hexagonal prisms. And chemists tune the conditions of nanoparticle growth to preferentially get one shape over another. They cannot really change the crystal symmetry, but they can change conditions to promote or suppress the growth of different crystallographic facets. There are also post-synthesis techniques like colloidal etching that we can use to either eliminate some types of nanoparticles within a reaction product or to make our nanoparticles rounder. And here I would really like to say that during my research, I have enjoyed working with chemists. They do this very intricate synthesis, and they often end up with really interesting nanoparticle shapes that then I had the opportunity to try and model and understand their crystallinity. That was always very exciting to do.
That's really interesting. So, how do these changes in the geometry of the nanoparticles affect the properties of these materials?
Yes, so in this case, let's take guitar strings as an example. So when you pluck the string of the guitar, you provide a mix of frequencies that cause the atoms of the string to oscillate. However, there is only one frequency that will eventually last for longer and will dictate the sound that we hear. So in a similar way, like I discussed earlier, when we shine white light or on our nanoparticles, their electrons will oscillate at certain frequency, and the particles will scatter light of that particular color. So if you have played around with a guitar before, you'll have probably noticed that when you change the material of your string, or you make it shorter, or if you pluck a string that is thicker, then you can tune that resonance frequency that we perceive as the pitch. So equivalently, by changing the material, the shape, or the size of the nanoparticles, we can tune their color. Let's take gold nanorods as an example. So these generally have two resonances. If we start to increase the aspect ratio of these rods, we can make these resonances further spaced apart in the wavelength spectrum. Also, if our particles have increasingly sharper tips, and this is really a fine detail that's actually important, we can push our resonances to redder colors. Another thing that's important is if we zoom really on the nanoparticle surface, we can see that this field enhancement is not uniform. And so around sharp features, such as corners, there are areas of really intense electric field. And so this is important. If we wanted to maximize the local field for better sensing applications, we would choose a sharp tip triangle as opposed to a round sphere.
So, with all of this information, how do you measure the changes in response to the nanoparticles, and how do you correlate these with their structures?
So we can use optical spectroscopies to measure the optical response of these nanoparticles as a function of wavelength, even down at the single particle level. However, optical microscopy is diffraction limited, and that means that we cannot see anything that's smaller than about half the wavelength of the light we are using for imaging, and that's about 300 nanometers. And the impact of this is twofold. First, we cannot really see with optical microscopy what is the shape or the size of our nanoparticles. And the second is that we cannot map properties that vary across our structure, such as the intense electric fields I mentioned earlier. So to overcome this problem, we can use, for example, scanning probe microscopies. So here, think of a very small needle that is sort of scanning across our sample. Or we can use electron microscopy, which is what I'm working on at the Foundry. And so in electron microscopy, we exploit the very, very short wavelength of electrons to resolve features down to the atomic level even. And in this way, we can get really beautiful images of our nanoparticles that we can then correlate to our diffraction limited optical measurements. We can also use various signals that stem from the interaction between our electron beam and our sample to map quantities such as electric fields or even the distribution of temperature. And here at the National Center of Microscopy, we have a brand new microscope that we are fitting with light injection capabilities so that we can do all these measurements under light illumination.
Thank you so much. So, with all this research that you have done so far, what are some challenges that you guys encountered?
First of all, I need to highlight that studying plasmonic nanoparticles and their optical response is inherently challenging because they are so small and the phenomena that are involved are also extremely fast. Think like trillion times shorter than a second. So to dive deep into the details, we really need advanced instruments. And as I mentioned just a minute ago, I'm currently helping develop light injection capabilities within an electron microscope, and a lot of the challenges we face are actually hardware related and related to understanding some of the phenomena we observe even before we actually try to measure anything on our particles. So, for example, since these microscopes are in high vacuum, we really cannot access our optical path components to align them like it's done in regular optical systems. So we we really need to devise new approaches to do this by looking at the output signals that are available to us. Another issue that we are investigating is why and how our sample drifts when we illuminate it with light. And this is important, especially in some cases, that because it limits our spatial resolution. One last thing that I should mention is that my work mainly focuses on characterizing and modeling plasmonic nanostructures and their response. And I'm some ways lucky that um, other collaborators have been providing the samples for me, but preparing nanostructures both via bottom-up and top-down approaches, and especially for materials that are not as well known, like magnesium and aluminum that I've worked with, can be very challenging. On the flip side, sometimes if sample preparation does not go as intended, we get to characterize some unexpected structures, and that can also be interesting sometimes.
That's really cool. So, on the other hand, what are some successes that you've had with your work?
Yeah, so before coming to the Foundry, I was really proud. I'm really proud to have contributed towards understanding the shapes and plasmonic response of magnesium nanoparticles. This was a new material for plasmonic nanoparticles that had just been introduced by my PhD advisor right before I started my PhD. And so that was really exciting. And I should highlight that magnesium's hexagonal close-packed crystal structure is really unique within the plasmonic metals. And we just discussed how shape is important in sort of controlling this light matter interaction. And so it was really, really interesting to find out the different shapes that this different crystal structure could support. Now, during my work at the Foundry over the last year, um, and in relation to the challenges that I mentioned above, we have done a lot of work in building our light injection hardware and have really thought outside the box, quite literally in this case, to figure out ways to monitor and manipulate our beam path within the microscope's vacuum chamber. And we also have a much better understanding of the light illumination side effects, which we are further sort of studying at the moment.
So, what are some next steps for this research?
Yeah, so with the setup we're building, we ultimately want to measure plasmon-induced temperature gradients in pairs of aluminum nanorods that are fabricated by our collaborators. And the impact of this experiment is twofold. First, it will determine the spatial and temperature resolution we can achieve with our setup. And second, it will provide a platform for studying photothermal heating in plasmonic nanoparticles. And also, aluminum has some interesting characteristics in its electronic structure. So we also want to investigate these and how they affect this heating behavior.
What is the importance of using these alternative metals rather than gold or silver?
Yeah, so this is a good question. So, in addition to their optical response, each material brings with it a unique combination of properties. And as we design plasmonic nanostructures for various applications, I think this is really important to take into consideration. So, beyond the fact that gold and silver are expensive, silver nanoparticles, for example, are cytotoxic. That means our cells don't really like them. Gold does not operate in the full visible range, only above about 500 nanometers, and this means that, for instance, it cannot harvest the full light spectrum of the sun. So, in contrast, for example, magnesium operates across all light wavelengths and has great potential for biocompatibility since we need to take magnesium as a daily dose, right? And so our body knows how to deal with it. That being said, it comes with other challenges in being much worse in its plasmonic response, and it's also very reactive. Another example that is relevant to my work is aluminum. So aluminum has a unique combination of plasmonic response and a large thermal expansion coefficient that makes it really the only suitable plasmonic material for studying plasmon-induced heating with the electron spectroscopy approach that we are developing. And so it really boils down to the specific application requirements. And so it's always good to have a pool of materials that we can sort of choose from.
That's really cool. So, what do you think is the big picture of your work, or how might it affect everyday life in the future?
Yeah, I think from my current work, the most exciting aspect is the development of instrumentation that allows us to probe materials with electrons, giving us atomic scale resolution, while simultaneously exciting them with light. My work has focused on the fundamentals of plasmonic materials that have great potential as biosensors, localized heat sources, or even sunlight energy harvesters, for example, in photocatalysis. However, beyond plasmonics, there are also many materials that interact with light in fascinating ways, from semiconductors to two-dimensional materials, and the instrumentation we are developing can give us a new window into understanding those interactions on the nanoscale. Also, the instrument we are working on is housed in the Foundry, right? And this is a user facility. And so that means that it's going to be accessible to researchers both from academia and industry, enabling a range a wide range of projects in this way. And so we hope that it will become a platform for advances not only in our fundamental understanding, but also to help design better materials and devices that rely on light matter interactions.
All right, that's all the questions I have for today. Thank you so much for joining me. I really enjoyed hearing all about your research.
Thank you so much for having me.
For those of you watching, if you're interested in hearing more about research at the Molecular Foundry, stay tuned for more episodes of the Foundry Fireside.